So let's take a look at how we would do homework number 4. We're going to walk through a comparable type of problem set up in exactly the same way. So we have an individual named Mark who gets a blood test for a particular type of disorder. The blood test can diagnose him with a disorder or without it. So he has the disorder or he's not. Those are the two possible outcomes of the blood test. In addition, Mark may actually have the disorder or he may not. And so that sets this problem up as a great example of signal detection theory. And if you remember, we looked at signal detection theory at the very beginning of the semester, and it is a great way for figuring out our hits, misses, false alarms. We can also think of false alarms as false positives, and correct rejections. These are the 4 possible outcomes of any test, of any time that you're trying to detect something. So this test is trying to detect, say, a type of cancer, and the test can be correct and say, yes, the person has cancer. That would be a hit. The test might incorrectly say that a person does not have cancer. It'll miss it. Or it can incorrectly say that a person does have cancer when they don't. That's the false alarm or false positive. Or it can correctly say that this person does not have cancer. That's the correct rejection. And so the question is, what is the likelihood that Mark has this form of cancer after he tests positive? And that's comparable to the homework question where you're trying to figure out what's the likelihood that Julia has cancer if she's one of the women who test positive for cancer. So our problem again here is really similar. The only thing that's different is the base rate here. That's the only thing that's different. For the homework assignment, 3% of the 100,000 women are expected to have cancer. That's the base rate of the disease. In this example, it's 5%, so it's just a little bit higher, but everything else is identical. And so one of the things we're going to see here is that when the information is provided in percentages, it can be really misleading. So if you're told that this particular blood test is 85% accurate at detecting the cancer in individuals who have it, then when you test positive, you will probably jump to the conclusion that you are 85% certain to have cancer. And we're going to see that that is absolutely not the case. We have 2 ways of thinking about this information. One way is using these percentages, which I think makes us jump to conclusions and biases our reasoning about an event like this that has a relatively low likelihood. This 5% base rate is a relatively low likelihood. If instead of using percentages, we figure out the actual number of people who test positive or negative, who get hits, misses, false alarms, or correct rejections, if we can figure this out in terms of numbers or frequencies, instead of percentages, we can do a much better job and we'll be less biased in our reasoning. So let's take a look. Out of 100,000 people, 5% will have this form of cancer. That's the base rate. So because of that, then we know that 5,000 people will have the disorder and 95,000 will not. These are the number of people who don't have the disorder. Now we can break that down into who gets correctly identified with the disorder and for whom does the test miss their cancer. So we know that the test is 85% accurate in detecting the condition in people who have it. So 85% out of 5,000 people, that's this 4,250. This is the number of hits. This is the number of people who are correctly diagnosed by the blood test as having cancer when they actually do have it. The remaining 750 people who have this condition are falsely told by the test that they don't have it. This is the number of people for whom the test misses their cancer or their disease. So this is the number of misses. So 15% out of this 5,000 people are falsely told they don't have the disorder when they do. Those are the misses. Now let's go down and look at the people who in reality will not have the disorder. Some of them will be diagnosed with it, some of them will be diagnosed without it. So the test has a 10% false positive rate. 10% of the people who are tested are going to falsely be told they have the condition when they really don't. So this 10% is coming from this large number of people, this 95,000 people who don't have the disorder. So 10% of 95,000, that gets us to 9,500 people. These are the 9,500 people who are tested and falsely told they have it. This is the false positive rate or the false alarm rate. And then 90% of the people who don't have the condition are correctly told they don't have it. So this is the correct rejection. So this is the number of people who receive a correct rejection, who are correctly told they don't have the condition. Now the question is, Mark is one of these 100,000 people, but he tests positive. So he's actually one of this group who tests positive. There's 4,250 who test positive who do have the disorder, and 9,500 who test positive who don't have the disorder. So a total of 13,750 people test positive. All 13,750 people are told they have the disorder. Mark is one of these people. What is the likelihood that Mark has the disorder? Well, we want to see what is that likelihood. So out of the 13,750 people, how many do have the condition? Oh, it's these 4,250. So 4,250 of the 13,750 have the disorder. So we can just divide, and that gets us to roughly 30%. So he has a 30% likelihood of actually having the condition after testing positive, which means even after he receives a positive test, he is still more likely to not have the disorder than he is to have it. Why? Well, has to do with our base rate here. The base rate of people who have the condition is relatively low. It's only 5%. So the great majority of people out of our group don't have this disorder. 95,000 don't. So that false positive, that 10% false positive rate is coming out of this very large number of people. And that's why a majority of the people tested receive a false positive, because that 10% is coming from a large number, whereas this larger 85%, it's a larger percent. Yes, the test is 85% accurate, but only in the relatively small number of people who do have the condition. So 85% of a small number is a smaller quantity than 10% of a large number. And that is why we are often very biased when we try to reason these things out using percentages. We forget the base rate. We forget that the 85% is coming from a small number and the false positive 10% is coming from a very big number. So it's much better to reason in terms of actually using quantities or frequencies. And then we keep it in perspective. And we can keep in perspective that out of the 13,750 people who do test positive, 9,500 of them will not actually have the disease. The majority of them will not have the disease. So to do the homework problem, you just want to set it up identical to how this blood test problem was set up. And so here's the blood test problem on the top. Here's the homework problem down here. The only thing that's different is the base rate. It's 5% for the problem that we just did. It's only 3% for the mammogram problem that you'll do for homework. Out of that 3%, of people who do have breast cancer, 85% will be correctly tested positive and 15% will be missed. And we can see those values here. So just fill in those values and then you should be able to do the problem in exactly the same way.